Dear students, uh, today we discuss the electric field due to uniformly polarized sphere. Actually, this is a fifth problem for point 2. Here the question is this one: find the electric field produced by a uniformly polarized sphere of radius capital R. Actually, a sphere whose radius is capital R. It is given that it is uniformly polarized. Therefore, this is the direction of the polarization. That is, this is polarized along this direction. This is the direction of the polarization P, which means here this will be the positive charge, this is the negative charge. Direction of polarization will be from negative to positive. Therefore, here it will be positive charges, and here it will be negative charges. And since it is uniformly polarized, then there will not be any bound charges that we discussed in the last lecture. Only the surface charge exists. These surface charges would give rise to a net electric field. The first question is, what is the electric field outside this uniformly polarized sphere? That is, let us say this is R is a point outside the radius. Next question is electric field inside the sphere, that is R less than R. Now let us address the first question, that is electric field outside the sphere. It is R greater than R. Let me draw the figure first. We are interested to find out the point that is outside. We need to find out the electric field at this point. For this, the tool that we have is this one. To find out the electric field, we can use this relation minus del V, because since the potential is a scalar quantity, then it will be quite easy to find out the potential due to this polarized sphere outside as well as inside. Then simply take the negative gradient, then we will get the electric field inside as well as the outside. To find out the electric field inside, let us write, outside, E out can be written as minus del V outside. Let me first consider, because this polarized object consists of a large number of dipoles, let me consider a simple dipole, one single dipole. It consists of minus q charge plus q charge. Its dipole moment is along this direction. Then at a particular distance r, at this point, the electric potential can be written as, due to this single dipole, let me write it as dV 1 by 4 pi epsilon 0 p dot r cap divided by r square. We already know the polarization P can be written as dipole moment per unit volume. Then the small p in this expression can be replaced using this expression P d tau. let me substitute here. Then this dv can be written as 1 by 4 pi epsilon 0 polarization P dot r cap d tau divided by r square. Okay. Now, to find out the electric potential at a point outside due to this whole polarized sphere can be easily find out. Just integrate this equation. This V outside can be written as integrate over volume 1 by 4 pi epsilon 0 polarization vector capital R cap divided by r square d tau. Actually, since the polarization P is uniform, that we can take it outside. This V out can be taken as 1 by 4 pi epsilon 0. P can also be taken outside. Volume integration r cap divided by r square d tau. Okay. This is equation number 2. This was our equation 2. Since the polarization is uniform, that P we have taken outside, then if I bring this P to the left side, this P V out by P is equal to 1 by 4 pi epsilon 0 volume integral r cap by r square d tau. This is nothing but the same equation. Now, in the case we were talking about the uniformly polarized sphere, where the positive charge will be here and negative charges will be here, the dipole moment will be from negative to positive. Therefore, the direction of the polarization is along the same direction, this direction. Okay, that is, the sphere is polarized along the z direction. Now, if I consider a sphere, another the sphere is a uniformly charged sphere. This uniformly charged sphere consists of a large number of charges, either plus or minus. Okay, that is, it contains a total charge Q and its radius is R and its volume charge density is rho. Then the electric field at a point that is R greater than R can be written as 1 by 4 pi epsilon 0 volume integral rho d tau divided by r square. This we have seen earlier also. We'll discuss later. We did a lot of problems on the uniformly charged sphere. Now the charges, this rho is the charges, free charges. This is not a polarized sphere, but this is a free charges. Then what I will do is, in this equation, if I take this is as a E out, rho is a volume charge density. If I take it outside and bring it to the left side, since this is I can write this equation as a E out by rho. Since it is a free charges, I will write rho f, because here we have the bound surface charge density rho b, but here the rho bound charge is 0. Okay. Now this can be written as 1 by 4 pi epsilon 0, and if you write in the vector form, this will be r cap will be there. Okay, then I have taken this rho of the left side, 1 by 4 pi epsilon 0, and this will be r cap divided by r square d tau. If you compare the right hand side of the equation 2 and equation 3, the RHS of both equations are same. Therefore, compare equation 2 and 3, RHS of both equations are same. Therefore, I can write this V out divided by polarization vector P is nothing but this E out divided by rho F. From this we can find out V out. That is E out by rho F into polarization vector P. Now here I will see what is the exact form of the electric field outside a uniformly charged sphere. For this uniformly charged sphere, if Q is the total charge, then the electric field outside the sphere can be written as this E out 1 by 4 pi epsilon 0 Q divided by R square. Okay. Here Q is a total charge contained in the sphere, where Q is a total charge contained in the sphere of radius r. One can easily write the electric field in terms of the volume charge density rho and in terms of the radius r. That I will do it here. The rho can be written as total charge contained in the body divided by the volume. Therefore, this Q can be written as 4 by 3 pi r cube rho. This is the rho F, free charges. Therefore, this electric field can be written as here what I will do is I will substitute this Q in this expression. Therefore 1 by 4 pi epsilon 0 is there. Then Q, instead of Q I substitute 4 by 3 pi r cube rho F into 4 by 3 because rho of here, if it is a vector quantity, I put r cap rho F r cap divided by this r square. Here the few terms will cancel, pi will cancel, here I missed this 4, for this 4 will also cancel, then this rho Q will not be there, the remaining terms will be rho of r cube by 3 epsilon 0 r square. That is, can be written as r cube rho F divided by this 3 epsilon 0 r square, the r cap. This is the electric field outside. If I write this is equation number 3, this is equation number 4, and this is equation number 5. Next I will substitute this equation number 5 in this equation number 4. That means I will replace this E out by this expression. Therefore, I can write our equation V out. V out, instead of E out I substitute r cube rho F divided by rho F 3 epsilon 0 r square into P dot this r cap divided by this r square. Okay, here this rho F and rho F will be cancel out. Now I can write this equation as this r cube is there, this P polarization vector P dot r cap divided by 3 epsilon 0 r square. Here I write this is equation number 6. This P dot R cap can be written as P cos theta, because R is a unit vector along the direction of R. This is a unit vector along the direction of radius vector R. This will be the unit vector along the direction of radius vector R. Therefore, I replace this P dot R by this P cos theta. Therefore, this V out can be written as P this R cube cos theta divided by 3 epsilon 0 R square. This is equation number 7. As I have mentioned earlier at the beginning, that is, electric field outside can be found out using this expression, and now we obtained the expression for the potential outside the uniformly polarized sphere. Now substitute this equation 7 to this equation. That is, we can write, therefore our aim, that is to find out the electric field outside the uniformly charged sphere, minus del V out. Now here this del operator has to be written in terms of the spherical polar coordinates. This del can be written as in terms of the spherical polar coordinates, dou V by dou R cap plus 1 by R dou by dou V by dou theta cap plus 1 by R sin theta dou V by dou phi cap. Now let us substitute this expression to this equation. Therefore, we can write this E out can be written as, take the minus sign outside, dou by dou R. Here there is a R dependence of this potential. Therefore, this is nothing but P, instead of V, substitute this one, P R cube cos theta divided by 3 epsilon 0 R square R cap plus 1 by R. Here theta component is also there, that is P R cube cos theta divided by 3 epsilon 0 R square theta cap, and there is no phi components in this expression. Of course, the derivative of this potential with respect to phi will be 0. There is no phi component. Now proceed with the differentiation. Here P R cube cos theta by 3 epsilon 0 is constant, that you can take it outside. P R cube cos theta divided by 3 epsilon 0 dou by dou R of R power minus 2, that will be minus 2 by R cube, the R cap, plus 1 by R. Here P R cube by 3 epsilon 0 R square is constant. Oh, here I missed it. To write dou by, here this dou by dou theta is there. That is P R cube divided by 3 epsilon 0 R square is common. It's constant, take it outside. Derivative of this cos theta with respect to theta, it is minus sin theta cap. Okay, if you look at this term here, P R cube by 3 epsilon 0 small r cube is a it's a common term. Here also p r cube by 3 epsilon 0 r cube. Then if you take it outside with a minus sign, then the remaining thing will be inside the bracket. The 2 cos theta will be here, and here will be the sin theta, theta cap. Let me write this in the next step. That is E out can be written as, if I take the minus sign will cancel, that is here if I take it outside, this is p r cube, p r cube divided by 3 epsilon 0 r cube. Then inside cos theta r cap plus here sin theta, theta cap. This is the final expression for the electric field due to the uniformly polarized sphere. Electric field outside uniformly polarized sphere. Now our aim is, let us do the second one, that is electric field inside the sphere. Electric field inside the sphere. Here R is less than R. This is our polarized sphere. Then this is our radius R. Now the point of interest is here. What will be the electric field inside this sphere? That is E inside can be written as negative gradient of V inside. Okay. As I mentioned, potential due to a single dipole at a distance R, 1 by 4 pi epsilon 0, which is a dV, this can be written as P dot R cap divided by R square. Now this R is inside the sphere. R is less than R. In terms of the polarization vector, this can be written as, this P is a P by d tau. This P is polarization capital P d tau. Substitute here, then we can write potential inside the polarized sphere can be written as integration over volume. It can take 1 by 4 pi epsilon 0 outside. This is polarization to P R cap divided by R square d tau. Since the polarization is uniform, I can take it outside. This V is equal to P 1 by 4 pi epsilon 0 volume integral R by R square d tau. Okay. Earlier we have seen that this expression is nothing but this term can be written as E inside divided by rho f. Actually we have proved here that is 1 by 4 pi epsilon 0 R cap by R square d tau is nothing but E out by rho f. Here similarly we can write this term as a E inside by rho f. Now I can rewrite this equation. V in can be written as P dot E inside divided by rho f. Let me put this is maybe equation number 1 and this is equation number 2 in this case. Here E inside means the electric field intensity inside is uniformly charged sphere whose radius is R, and the charge contained within a small radius R That charge can be written as Q inside. Okay, I will rewrite this electric field in terms of the volume charge density. There is a volume charge density rho f can be written as total charge enclosed by the small radius r, small r, that is Q inside, divided by its volume, that is 4 pi 3 pi, that is charge enclosed by this small radius r, r cube. Therefore, the electric field inside can be written as E inside is equal to 1 by 4 pi epsilon 0 Q inside divided by r square. I am going to replace this Q inside as a rho f into 4 by 3 pi r cube. Therefore, E inside can be written as 1 by 4 pi epsilon 0 instead of Q inside rho f into 4 by 3 pi r cube divided by this r square. Here this 4 pi cancelled, r square r cancelled. This is a rho f, r rho f divided by 3 epsilon 0. That is, this E inside can be written as rho f r divided by 3 epsilon 0 r cap. Now I am going to substitute this expression here. Okay, if I put this as equation number 3, I will substitute equation 3 in equation 2. I copied equation 2 and equation 3 to the new page, and here substitute 2, put 2 in, put 3 in 2. Therefore, V inside can be written as P dot rho f or r cap divided by, here 3 epsilon 0 is here, and rho f. This is rho f get cancelled. This can be written as P dot product can be replaced by cos theta. Here r will be there, PR cos theta divided by 3 epsilon 0. This is V inside. Now, we have considered that our sphere is uniformly polarized along the z direction. It's from negative to positive. It is along z direction. In the spherical polar coordinate system, the z can be written as r cos theta. This is a direction of polarization. Then this V inside can be written as V inside is equal to, instead of this quantity I will write Z, P capital polarization PZ divided by 3 epsilon 0. The electric field inside can be written as, take the negative gradient of this potential, just substitute this equation to this one, where this del can be written in terms of the Cartesian coordinate because we have the z in Cartesian. This can be written as minus dou by dou x I cap plus dou by dou y j cap plus dou by dou z k cap, and the potential V, that is Pz by 3 epsilon 0. Now here the potential depends only on the z. Therefore, this electric field inside can be written as minus of derivative of dou by z of P, that is P by 3 epsilon 0, minus P divided by 3 epsilon 0 along k cap. K cap means If I consider this is a x direction, this is z direction, this is a y direction, then along z direction we can take it as a k cap, this is a I cap, this is a j cap. Okay. Now let us say this is the electric field produced inside the uniformly charged sphere. We obtained the expression for the electric field inside for polarized material minus polarization P epsilon 0 k cap. Okay, let me draw the electric field lines of this polarized object. This is our polarized object. Its polarization is along the positive z direction. That means our dipole moments are oriented along this direction. Polarization. Therefore, the positive charges will be here and negative charges will be here. Now let us see how this can be described. The surface charge density, because of this uniform polarization, can be written as polarization vector P dot n, where n is the unit vector along the radius vector. This is r. The unit vector n is along the radius vector. Let us write small r cap. This r can be anyway, any point on this sphere, maybe here, maybe here, 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 here. But this r vector is along the radius vector r. This polarization P can be written as this is along z direction. This z coordinate in spherical polar coordinates can be written as r cos theta, and this n cap, since it is along the r direction, let us write r cap. This can be written as P, if I substitute z here, cos theta r dot, this n cap can be replaced by r cap. This is nothing but P cos theta, that is a surface bound charge density. Okay. Since this polarization is along this direction, this z direction, I need to find out the amount of charge density on each point on this sphere. For this I can use this relation. This theta is the angle between the z direction, that is polarization direction, and this r vector. Okay. This r vector can be any direction, but this z is the polarization direction is fixed, that is around z direction. To find out the bound charge density at this point, both the r and the polarization vector both are along the same direction, that is theta is equal to 0 at this point. Since theta is equal to 0, this cos theta will be plus 1, it is positive. This bound charge will be maximum, that is, this will be a larger amount, this point. And at this point, that is, polarization is along this direction, the r vector is along this direction, therefore this angle theta is slightly larger. Theta becomes maybe 30 degree, then 10 degree, 20 degree, 30 degree, 40 degree, 45 degree, and this is 90 degree, and depends upon this angle theta. So for example, this is a 10 degree, this is a 20 degree, this is a 45 degree, and then this is a 90 degree. For these angles, the cos theta will varies. That is when theta tends to 90 degree, which means at this particular point, let us say the cos theta will be 0, sigma will be 0. Which means as we go from the theta is equal to 0 position to theta is equal to 90 degree position, the value of sigma will increase from maximum to 0. That is from theta is equal to 0 when it goes to 90 degree, then 0, 10 degree, 20 degree, 45 degree, 90 degree, then 180 degree. Cos theta value, let us see that cos theta value starts from plus 1 to 0 to minus 1. Accordingly, this sigma 0 minus sigma will be there. The charge density will be a larger value will be at this point. It will be smaller, 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 and it reaches 0 at the equator. Here sigma will be 0, sigma will be 0. Then here also slightly, you see, after this cos theta will be a negative value. Once it is a negative, sigma will be negative charge, and its strength increases. Here it will be plus sigma, that is here it will be negative charge will be, amount will be larger, smaller again, smaller, smaller than 0. Here also on the side plus will be larger, then it goes to smaller, smaller, smaller. Okay, that is a 0 is at the equator. If you draw the electric field line, see the electric field line starts from the positive charge and ends on the negative charge. I can draw this electric field lines in this way. This is the electric field line. From the expression you can see the electric field line is opposite to the direction of the polarization. Electric field is downward, polarization is in upward direction. Then what about the electric field lines at the side charges? That start from the positive and ends on the negative. Ends on the negative. Okay. Here also starting from the positive and ends on the negative. Okay, in this way. Okay, this is a picture of the electric field lines due to a uniformly polarized sphere. The volume bound charge density will be 0 because in the case of uniform polarization, here large number of dipoles will be there, positive, negative, and those will be cancelled out. Positive, negative. These charges will be cancelled. Therefore, there won't be any total volume charge density will be 0 in this material. Rho will be 0. Only the surface charge exists. Therefore, rho B will be 0, but surface charge density will be present. Okay, thank you very much for watching.